Welcome back to the course of chemical crystallography. In the previous lecture, we have discussed about the data processing and how to derive the expression for the relative intensity from absolute intensities. And then during this process, we were talking about how to understand or how to account for the thermal vibration using the thermal vibration parameter B, the mean square amplitude of atomic vibration, and we have discussed that the atomic scattering factor with vibration falls more rapidly compared to the situation where there is no vibration or at 0 Kelvin temperature. And then depending on various values of B, we have discussed how the scattering factor falls with increasing how the scattering factor falls with increasing temperature, and then on lowering the temperature the scattering factor reaches the maxima at when B equal to 0. So then we try to understand how one can do the relationship between I relative versus I absolute, and in that process we have ended up seeing a plot called Wilson plot, which is given here. This Wilson plot is generated to identify a good data set from a bad data set, and also to identify the corresponding constant, the scale factor or the scale constant which is related to this C. So ln C is calculated from the data by extrapolating it to sin theta by lambda square equal to 0. And the slope of this straight line gives you an estimate of the thermal parameter B. So in today's lecture, we are going to now discuss about two more aspects where we will now try to see how one can identify the correctness of the lattice parameters, whether it is monoclinic, orthorhombic or something else, and how then one can identify the symmetry elements like inversion symmetry, two-fold symmetry and mirror symmetry, which do not cause any systematic absence, but it gives you an indication of these symmetry elements present in your lattice through the values of IHKL that we are going to record in case of a crystal data. So today we would like to learn, the first point is how to identify the correct Bravais lattice from the measured IHKLs. See, there may be situations when we try to index some X-ray diffraction pattern, we may get the values of A, B, C, alpha, beta and gamma from a set of initial reflections. On physical observation, it may turn out that A is very close to B and is not equal to C, and alpha equal to beta equal to gamma equal to 90 degree, which may look like it is a tetragonal system. Is it so? Is it true that it is a tetragonal system? Or from the initial measurements, it may look like A not equal to B clearly, not equal to C very clear, alpha equal to gamma equal to 90 degree is also very clear, but beta is very close to 90 degree, maybe 89.9 degree or 90.1 degree. So the confusion is it monoclinic or orthorhombic? This confusion cannot be solved at the beginning when we are trying to determine the unit cell, because we do not have enough number of reflections to talk about, and we have not reduced the data to get the relative intensities of all HKL values that are going to be recorded during the data collection. So once the data is collected, these parameters are redetermined. And what is done is that then we compare various IHKL values. To identify the crystal system more accurately. So at this point, after the data reduction is done, once again re-indexing of the lattice is done, the re-indexing of the unit cell is done, and then one looks at the statistics of all the HKLs and tries to see what kind of information can be found from those reflections. Say for example, in case of a monoclinic lattice, for a monoclinic lattice, we should have IHKL equal to I H bar K bar L bar, which is Friedl's law, I H K bar L, which is the mirror operation, and the corresponding Friedl's law, Friedl's opposite is I H bar K L bar, which is a twofold operation parallel to B, and for I H bar K L set of reflections should have the corresponding equivalence with I H bar K bar L bar. Then you apply the mirror symmetry, so it is H bar K bar L equal to I H bar I H K L bar. So if we see that in the data that we have recorded, these two set of equivalence is met, then we conclude it as monoclinic. So this confusion is avoided, that whether beta, when it is close to 90 degree, should we consider it as beta equal to 90 degree, or we take it as beta equal to something like 90.1 degree or 90.08 degree, which is very close to 90 degree. So in case if it is really monoclinic, then these two conditions will be met. If it is not monoclinic, if it is orthorhombic, then a different condition will be met. And what is that different condition? In case of orthorhombic, what we know is that the reflections which are HKL corresponding Friedel opposite I H bar K bar L bar, and orthorhombic has mirror symmetry, that is MMM symmetry in the Laue group. So it should have the equivalence as I H bar K L equivalent to its Friedel opposite I H bar K L bar equal to I H bar K L equal to its Friedel opposite I H K bar L bar is equal to I H K L bar should be equal to I H bar K bar L. So all these 8 group of reflections 1, 2, 3, 4, 5, 6, 7, 8, all these 8 group of reflections will have the same relative intensity, and this will then conclude, okay, what beta we were seeing very close to 90 degree is actually 90 degree, hence we take it as orthorhombic cell, because this step is very important. If we do not determine the correct crystal system, which then would be taken to find out the systematic absence conditions to determine the space group. So if our unit cell that we are determining here is not right, we will fail to determine the correct space group. So the systematic absence condition will fail to determine the correct space group. What can happen in turn? Because of incorrect space group, no structure solution. Because our structure solution in general works based on the space group that we have determined. Of course, nowadays XT, the modern latest version of ShellX, can do structure solution without the correct space group being determined. It determines the structure based on space group P1 and then applies the different systematic absence conditions observed and then applies a suitable space group and then gives us the solution in appropriate space group. So now the other point that we would like to highlight here is the situation when A is very close to B and is not equal to C with alpha equal to beta equal to gamma equal to 90 degree. In the same way, we need to see whether it is tetragonal or not. So for that, we should look for reflections which are IHKL should be equal to I H bar K bar L bar should be equal to I KHL should be equivalent to I K bar H bar L, and the other conditions which comes for the tetragonal symmetry, which could be either 4 by M or 4 by MMM. So one has to look at those IHKLs corresponding to different point groups, the different Laue groups of Laue groups of tetragonal system, and see those equivalents are met or not using this particular data. If those equivalents are not met strictly, then it is orthorhombic. That means the interchange of axis A and B is not allowed. If all these conditions are met together, then it is tetragonal. See here what I have written, KHL, what does it mean? Suppose I am talking about a reflection I 3, 2, 1 should be equivalent to I 3 bar 2 bar 1 bar, which is Friedel opposite, then it should be equivalent to I 2 3 1, that means A and B interchanged, and the corresponding Friedel opposite I 2 bar 3 bar 1 bar, and so on. So this is what is meant by KHL or K bar H L bar, K bar H bar L bar, because the indices get changed but the numbers remain the same. So this way one can actually identify the correct Bravais lattice at the end of data reduction. So now we would like to see what happens if we have a center of inversion or if we do not have a center of inversion. So what we know is that in general, for all the light atom structures, Friedel's law that is IHKL is equal to IH bar K bar L bar is strictly followed for both centrosymmetric and non-centrosymmetric structures. But for structures containing atoms like sulfur or heavier tend to show deviation from Friedel's law to some extent. So then it becomes easier to identify the centric and non-centric structures by looking at the IHKL and IH bar K bar L bar. So what we need is a careful observation of the intensities IHKL can indicate the presence of, or rather presence or absence of I in a structure. To determine the presence of this inversion center in a structure, there are a few different methods that are known in the literature. So now here I am going to discuss one such method which is called the Z test or NZ test, and it was introduced by Howells, Phillips and Rogers in 1950. It was introduced in this Acta Crystallographica journal, volume 3, page number 210, year 1950. So what they proposed is that from the general observation that the intensities for IHKL are more tightly packed for non-centrosymmetric structures about the I average, whereas the IHKL values are more deviated from the I average value for the centrosymmetric structures. So what they tried to do is that they calculated the number Nz, which is the fraction of reflections less than a specific value of Z, where Z is nothing but the ratio of the corresponding IHKL to the average IHKL. So first we need to see the value of Z for each and every reflection. It is the ratio of the intensity of individual reflections intensity of individual reflections by the average intensity, and then they propose to plot these two quantities against each other, where one is plotting Z along x-axis and the corresponding Nz along y-axis. So then it was shown that for a non-centrosymmetric structure, the line is more straight compared to the centrosymmetric structure which is bent. So this observation is made from the data set that was collected and reduced, and then the corresponding relative IHKLs are taken into account. The IHKL average is done, and you take the ratio of those IHKL with respect to the average. So we calculate the value of Z, and then from there we calculate the fraction of reflections less than a specific value of Z. That means the specific value of Z can be made to fall within 0.1, 0.2, 0.3 and so on, 1.0. So the number of reflections, that is Nz, is the fraction of reflections having the value less than Z of 0.1 is then plotted, and a best fit line is done. So in case of centrosymmetric structure, it may be the case that the points were falling like that. So the best fit line represents a straight line, whereas for a non-centrosymmetric structure, these lines indicate a deviation from a straight line and rather go like a curve which is drawn here. So the best fit curve that goes higher than the non-centrosymmetric structure, and from there one can conclude whether it is centrosymmetric or non-centrosymmetric. To understand this, let us take one example. Suppose in this particular example, suppose in one data set we have the corresponding HKL and the IHKL values from the data reduction software. We have numbers for 001, 002, 003 and so on, reflections up to 00n. The values may be something like, for example, 300, 200, 400, like that. This may be 600, the somewhere in the middle the maxima may be 1000 and so on. And then the set of reflections where it is 010, 020, 030 and so on with 0n0 also has values very similar like 280, 210, 410, somewhere in between you have 990, somewhere here you have like 610 and so on. So then we may find that let the average, that is I average, is equal to say 500. So we calculate the Z for each and every reflection with IHKL by 500. So that is my value of Z. So Z can be greater than 1 or less than 1 depending on the actual intensity of IHKL. So now we find the value of NZ, that is the number of reflections that has Z value less than 0.1, less than 0.2, less than 0.3 and so on, and make a table. So what we are getting is we have Z and NZ. Say for Z equal to 0.1, 0.2, 0.3 and so on, we have some numbers here, and then we plot those two quantities against each other and we end up getting a plot like this. If we get a plot in this manner, then we would call it as centrosymmetric. If we get a more or less straight line, we can call it as, we will recognize it as non-centrosymmetric. And here at this point, I would like to just sensitize you that there may be something which is called hypercentric. The hypercentric structure means that there is no center of symmetry in the lattice, but there is a center of inversion in your molecule or in a pair of molecules which are there in the lattice. So you have a pseudo center of symmetry in your lattice. So in that case, this statistics will show a very minor deviation from non-centrosymmetric plot, but it will not be as deviated as like centrosymmetric. So it will go nearly a straight line, but with some curvature in it, and it will, then you identify it as hypersymmetric structure. So this happens when either your molecule has a center of inversion, but that center of inversion does not lead to a centrosymmetric structure, or that center of inversion does not coincide with the center of inversion of your lattice. In that case, you end up getting an hypercentric distribution. So in this lecture, we have learned how to identify from the intensity statistics the correct unit cell parameters, how to identify the correct Bravais lattice, that is whether it is the rather correct crystal system, whether it is monoclinic, orthorhombic or tetragonal or anything higher symmetry, and then we try to understand how one can identify the presence of inversion center in a crystal. So in the next lecture, we will discuss about the study of these IHKL values, from which we can then identify the presence of twofold and mirror symmetry in crystal structures.